Okay, so yeah, today is split up into two different types of deep learning frameworks. One is convolutional neural networks, which we typically use for image classification. In the afternoon, we'll look at recurrent neural networks, which look at sequence data. I suppose before we dive into convolutional neural networks, yeah, we should talk about deep learning first. So do the slideshow. There we go. So yesterday we were talking about neural networks, and if you just recall that what we do is that we send data forwards through the network, and we have some activation functions in there. And then right at the end, we have our output neuron, where we can compare what the network is saying, which will always be terrible, usually in the first run. We compare the ground truth to what we're predicting currently. So just the first run, it will always be terrible. But what we can do from here is, by comparison, we can determine our error or loss. Some people use the word cost as well. Don't worry about it. Error, loss, costs, all the same thing. The thing is that we can compare how it's doing across each epoch or every run through the network. And going backwards, we need to update our weights. So once we've arrived at our output neuron, what we were saying is that this is how much we were wrong by, and we need to tell the weights to update themselves to tweak the neural network. You know, basically we're saying something like, you were wrong by this much. Please learn from your mistakes, go and change a few things. Come back after you've updated your weights, pass it forward again, and we'll recheck. So that's kind of, you know, what was happening in a neural network. You send things forward, you send your data forward, you make a prediction, you see how wrong you were using the loss function, and then update the weights by sending it back through the network. Yeah, so if you see loss, error, cost, and things like this, don't worry, they're just the same thing. I use them interchangeably depending on what I'm talking about. But the important point that Marcos was talking about, which is, you know, really what neural networks are using to help learn, it was gradient descent, and he played that game, finding your house at the bottom of the valley. And you know what we were saying is that if you take 2 points, so if you take your left foot top of the valley and put your right foot down in the valley, you know, you can't see where it's going because the fog's there. Once you've actually got 2 points, you can take a tangent to this curve. So if we look at, you know, the 2 data points between 3 and 5, using a bit of calculus, if you differentiate this curve between these 2 points, you'll end up with a tangent. And clearly this is a gradient, or it's a slope. And not all slopes are equal, because if we look at the slope between 6 and 8, it's a less steep slope compared to between 3 and 5. So, you know, gradient descent was just a tool to see, kind of measure, you know, how good the direction is of travel. So this is something that gets used for neural networks. It gets used for other algorithms, by the way. It's not just neural networks. It's not unique. You can optimize, you know, the maximum likelihood estimation in logistic regression. You can use gradient descent for that if you wanted to. So just to point that out. Yeah, but let's talk about this curve. So you know, back when I was doing about neural networks, this kind of really confused me, because I was like, well, surely this curve doesn't actually exist. We don't know what the cost function is. Remember, you can have these curves with local minima, global minima, and so on. And of course, you know, if you're given that curve, then, well, I know what to do, because I can see what the profile of this mountain or hill is, or valley is. But of course, that doesn't exist. You know, this is just approximating every time you go through the network and you measure your error. So we might have started at, with our weights giving us an output value of this, and it says we've got, you know, a lot of error here. If we updated the weights too much, we might end over here. And, you know, this curve gets mapped out by adjusting these weights thousands, tens of thousands of times. So you know, this curve is built up of small data points going along. So it's not something that exists. When, you know, we like to think of rolling a ball down a hill, but it's not quite that. So, yeah, there's no, you know, hill in inverted commas before we start training process. We can't see this in advance. So, what do? We need to differentiate something. We need some curve to find a tangent to. And of course we can do that because Marcos was talking a lot about the logistic function or various different activation functions. Again, Andy pointed out that sometimes the word sigmoid gets used interchangeably, especially if you're using TensorFlow, because that's the name you call for it. But don't worry too much. The important point was that this logistic function, it was a curved function, which we've seen in logistic regression. It squashes the output between 0 and 1. There are other similar functions, the tanh function, which squashes outputs between -1 and 1. But the point is, this is a curve that we can differentiate. So when we say something like, we're going to take the derivative of the weights with respect to the error or the loss function, what we're actually doing is we're taking the derivative of the activation function. And of course, the weights come into an activation function, whether it's going forwards or backwards through the network. And it's multiplying all values. Remember, all these neurons are connected, so they all multiply against each other. They get fed into an activation function. And what we're saying is that this activation function, say a sigmoid, we take the derivative of that. And as the values go in, we have to take into account the output values. They've gone through the derivative of the activation function. So they're not going to be values between 0 and 1 anymore. Because, well, as we'll see, the sigmoid function or logistic function is there in blue. If you take the derivative of the sigmoid function, you get this kind of profile. So there's a few important things to note with the derivative of the sigmoid function. We've got whether you're sending data forward through the activation function or back to update the weights. Whatever those values are, instead of being squashed between 0 and 1, so whatever value comes in along the x-axis, whether it's negative or positive, instead of being squashed between 0 and 1, it's going to be squashed between 0 and 0.25. So this is a theoretical concept, a derivative of the sigmoid or logistic function. Your values are squashed between 0 and 0.25. And if you look at large values of x are going to be small in the response. So if we have a value of 8, it's 0. And again, the magnitude of negative numbers, if they are large, then you will end up with 0 as well. So yeah, our raw sigmoid function squashes values x between 0 and 1, and just try and hold in your head these values for x. These are the inputs of all previous neurons being multiplied together and going into this activation function. So we'll have some number that comes in, x, and usually what we were saying is it'll be the response will be between 0 and 1, but now it's between 0 and 0.25. So when we are updating our weights, we're coming backwards through here. What we would like our neural network to do is have the ability to update our weights a small amount, if we think we need to update it by a small amount, or even a large amount if we need to do that. If we sent our data through the network using forward propagation, we compared the error and it was large, we might want to update the weights in a large way. But when we do back propagation, send these weights through, what we're saying is our error is coming in from the right-hand side, doing back propagation. Our error is coming in, and we need to say, we're going to send this error through this derivative of the activation function, and the resulting value is how much we want to update our weights by. And so I think you can see a slight problem, because if you want to update your weight, by nothing, so the value, there's no the error coming in is 0 into this neuron. What you're saying is update this weight by a huge amount, but that's not ideal. of course. And also the bigger problem, which is what we're gearing up towards, is small values coming in. You're not going to be able to update the weights by a lot because the response is small. So very small values or very large values coming in of error. You're not going to update the network as much as you want. And because the error is back propagated through the derivative, the weights as you go backwards get updated between some value between 0 and 0.25. So this squashed between 0 and 0.25. And in deep neural networks, which is what we're gearing up to, you keep doing this repeatedly. You take the error from the output node and you have to back propagate it through all of the neurons, all of the layers. If you keep doing this, you start ending up multiplying a chain of numbers where the numbers all between 0 and 0.25. And this causes a problem because, if you think of a quarter of a fifth of a quarter of a tenth or so on, we end up updating the weights by a really small amount. And you might think this is fine because over time, we don't want the weights to keep updating. We want to arrive at some value. We want to converge and say, look, our neural network is perfect now. And we can see that because we are not updating the weights anymore. Like, in maximum likelihood estimation, you just find that where you converge, where the expected values that you're trying to plot the distribution against, that doesn't move anymore. Or in k-means, we were looking at the intercluster error. When that stops decreasing, then you finished. But we know that the cost function, or the cost profile, the loss function, if you like, is not as simple as just one value. We know it's likely to be the fact that you have lots of these local, global minimum, and so on. So we end up with points where the weights don't update themselves after a certain amount of time because of this unique property of the derivative of a logistic function. So over time, the amount to update the weights by becomes so small that the network, if it needs to, becomes unable to correct itself or improve itself any further. So what you find is that logistic activation functions, it's really difficult for them to overcome things like local minima problems, purely because it finds it difficult to update the weights. So especially the weights right at the beginning of the network. Remember, we take the error from the right-hand side and we start propagating through. By the time you've got down to a quarter, fifth of a quarter, of a tenth, or whatever, the weights at the start of the network, they've just hardly been updated at all. So this is called the vanishing gradient problem. Over time, the values of our gradient, because we're going through the derivative function, is become so small that we can't update our weights anymore. And this is an issue. It's not too bad if you've got quite a shallow network, but we're going to be talking about deep learning. And deep learning, all it is not some crazy thing which is completely different to neural networks. It's just a very deep neural network. So what we find is that sigmoid functions, they're good because they're non-linear. And remember, we're often solving non-linear problems. And they're non-linear, and we can take the derivative of a non-linear function, like a curve, so we can get our nice tangents between 2 points. So that's good. And we can do things like map out a loss function doing that, which is handy. But we get this vanishing gradients problem over time. So the network ends up getting stuck. So what we thought once was a really good idea, and for years and years, sigmoid functions were at the forefront of neural networks. When we come up with more difficult problems we want to solve, I'm thinking now of things like Tesla, automated cars, things like this. Chest ray scans. Hopefully we'll get to look at chest ray scans today. I'm just running a notebook now and it's very slow at the moment. These sigmoid functions were designed to solve complex problems, but as complex problems, the data required is huge and you need deeper networks to solve the problem. They start to fall down. So is that pretty clear so far what the vanishing gradient problem is? The fact that because of the derivative of the sigmoid function, we start to just decrease our gradients over time. And, gradients are the things we need. Gradients allow us to measure in a certain direction how good is it that we're going in this direction compared to maybe a different direction? If you can't take derivatives through your network because the gradient's so small, you just end up being stuck. The neural network doesn't do anything. So is that pretty clear?
Yeah, that seems clear for now.
Okay, good. So obviously this problem is really bad for deep neural networks or deep learning frameworks. How many layers you need to be a deep learning framework? It's like a cutoff. There's a threshold. We talk about thresholds all week. There's not just a switch where you go from vanilla neural networks or perceptrons to a deep learning framework. This could be considered a deep neural network. Typically, I think some of the notebooks we're using, they might have, I think one's got 4 layers and one's got 8. But the point being is that, as you can see, error is getting back propagated and multiplied together. So at this point here, all of the inputs are being multiplied from all these lines, and it just gets smaller and smaller and smaller, the grain. So by the time you get back to, okay, how much I need to update the weights from this node, it's just is negligible over time. So yeah, actually deep learning is quite new. We've talked about a lot of these machine learning algorithms that they're quite old. Conditional probabilities Bayes theorem, that was, if I remember off the top of my head, 1758, and the ideas behind neural networks, they go back to the 50s. And so this problem went unsolved until about 2010. There was actually 2 papers in 2009, 2010, but I think Nair and Hinton, they proposed a different kind of activation function, and they didn't invent this activation function. Again, this activation we're about to talk about was invented in the 80s. But they proposed using a certain type of activation for neural networks to try and solve this problem of vanishing gradients. And Andy mentioned this yesterday. So it's called the rectified linear unit, or ReLU. And we're going to be using these. I'm just eyeballing the notebook now. We're going to be using ReLU for our deep learning frameworks. It's not the only activation function. There has been others since, but this is really the first activation function when Nair and Hinton decided there's this existing function. Why don't we try plugging this in? So let's try and understand what a ReLU activation function is. So I've put it side by side with the sigmoid function, which we all know and love. So ReLU is this, and it looks strange. It's like, it just looks like a cheat to me, like we're cheating slightly, because the first thing that springs to mind is, don't we need a nonlinear function to solve nonlinear problems? So this is a nonlinear function. It comprises of 2 linear components. I will try and demonstrate in a couple of slides later how this is nonlinear and can solve those types of problems. So there's no curve though. I was telling you before that when we take the derivative of a curve, derivative between 2 points on a curve, we end up with a tangent. And quite clearly, if you took the derivative at any point along this ReLU function, there's no curve here, so there's going to be no tangent. In fact, if you take the derivative of a straight line, it's just the line itself. This is the reason why, just forget about this left-hand side of ReLU for a second. If we had just a linear activation function, which can range between minus infinity and infinity, if you took a derivative of that, it's just itself. So there's no real learning going on in that case. So that's why we don't use linear functions. No matter how many linear functions you chain together in a neural network, you won't get a non-linear solution. So it seems a bit weird at the moment. And we have these 2 properties. So if our value of x, and when I say x, this is the input, whether you go this way or this way, from all other previous neurons multiplied together. If our value of x is below 0, our derivative is 0. So the derivative of this is 0. If the value of x is greater than 0, then it's itself. Yes, I think we need to explain why ReLU is a nonlinear function, because I can see exactly what you're thinking. You're telling me that we can't even take a derivative, it's just itself. Surely we're back at this linear activation function problem. But actually, because of this kink in, and you can actually, this angle can change, by the way. You don't have to necessarily, you can have things like leaky ReLUs, which they will have this kink, which goes into minus numbers, or you can have positive numbers. So this kink, you can adjust the angle of your classification boundaries. So remember, in a linear problem, no matter how many linear functions you chain together, you will always end up with a linear solution. And this is tanh. So remember, this is almost like a sigmoid function, but you squash the values between -1 and 1. And you can see how it starts to curve a little bit. So it's not quite a straight line. As you keep iterating through, you end up with a circle. Well, ReLU, because it's clearly non-linear, because you have this this bend here, this elbow, if you like. If you chain together lots of these elbows, you end up like creating hexagons. And if you keep doing, I'm sure if you went up to epoch equals 500, you go 500 times through the network, you will end up with approximating a circle like this. And it's purely because, we have this bend here, and we do have control on how much we bend, depending on, as I said, the angle of this part here. So are you all okay on how ReLU can approximate non-linear solutions? If you chain lots of these together, all at slight angles, it does become a circle, you see. So ReLU, first thing, think of, it can provide non-linear solutions. So because we've passed that, we know, okay, great. So let's now go back to this derivative. Oh yeah, by the way, so there's a lot of people use these GELUs now. So instead of just having a hard angle, we're approximating hexagons. It just helps smooth this out even quicker using a GELU function. Yes, so hopefully you are convinced that ReLU can solve nonlinear problems if you chain lots of them together. But let's go back to this vanishing gradient problem. So remember, with the sigmoid, we were multiplying all of our weights together. It gets sent into the derivative of our activation function, and you squash that value between 0 and 0.25. And you're saying, as you come out the left-hand side, you're going backwards to the network. As you come out, we need to update our weights in the next, in the previous layer by some value between 0 and 0.25. But in ReLU, for one thing, the derivative is really easy. It's either itself or it's 0. And so it doesn't mean we can't take a derivative. And what we were concerned about with just using a linear function is when you take the gradient, you're just propagating the error fully, which is fine in itself, but you can't solve a non-linear problem. So the main issue with a linear function wasn't the fact that the gradient of it is itself. The main issue is that it just can't solve a non-linear problem. So, it was even quite nice that, the derivative is easy to calculate on a linear function. But here, as we've just said, that it's either itself or 0 in ReLU activation function, and it solves a non-linear problem. So this means that we don't keep squashing the values that we need to update our weights by between some value of 0 and 0.25. We either fully propagate the error through the activation function, so we're not like decreasing it over time, or you just completely get rid of it. So sometimes what you might find when you're reading about ReLU is it can create dead neurons. But I think Marcos briefly addressed this, that if a neuron becomes insignificant, the weights coming out of it into the next neuron is just so small and negligible. What you'll find is that the little information you would have learned, you still learn a little bit of information. You can still regain that information as you go through the network again. So you do get this slight issue of creating dead neurons, but we can fully propagate the error through ReLU. So this is good because we don't end up with this vanishing gradient problem with ReLU, and it can solve nonlinear problems. And I suppose the third benefit of this is that it's really quick. I mean, the derivative of a sigmoid function, you have to actually do a bit of maths there, but ReLU is just like a decision. You don't even need to do any math. You just say, oh, if the value is this, it's 0. It's like a step function in a way. So hopefully you're all okay with the fact that ReLU can solve nonlinear problems, and you're all okay with the fact that this vanishing gradient problem goes away with ReLU, and it's quick. So deep learning, because of this idea from Nair and Hinton that we can use this ReLU activation function, which was back in their paper in 2010, this was the advent of deep learning, and it was tied in with the ReLU activation function. So these really deep neural networks that we knew we needed, we'd saturated what we could do with neural networks. We knew with this data explosion over the last 20 years that neural networks just weren't enough. We knew we needed deeper networks because we needed to, if you think about, if I go back to this slide here, this is only 50 epochs through a network. This is not too bad, but if we wanted to turn this into a circle to solve a nonlinear problem, we'd have to have an even deeper network to do this. So this ReLU activation function allowed us to use these really deep feed-forward neural networks. Yes, there we go. So we're all celebrating now. We've got rid of this vanishing gradient problem. So is that pretty clear? How deep learning came about. When you hear the term deep learning, it's not just a whole different branch of machine learning. It's just a deeper neural network, and we couldn't do this until someone twigged that we could use this ReLU function. And it's not the only one that gets used now in deep learning networks. There's other you can use. So I know there's a whole buzz around deep learning, but it's just an extension of neural networks, really.
Another question.
Yeah, sure.
So the way or the kind of activation functions that have been described as of now, they seem to be very useful for classification and clustering like problems, if that's a correct perception.
So yeah, a logistic function, so sigmoid, if you think about logistic regression back at the start of the week, yeah, they are really useful on their own in classification because they normalize things between 0 and 1, i.e. probabilities. We're in probability land there. And you can choose a threshold, say low or greater than 0.5 to get a classification boundary, but you also get the probability out as well. So they are useful in their own right, but it's just when you come to plot it, building deep neural networks, because this unique phenomenon of the vanishing gradients problem, they become less useful.
So is there some kind of an activation function or just another way to approach the neural networks, or deep learning rather, for predictive analysis, but rather than just simply classification type problems?
Okay, yeah. So I'll give you an example of how you can turn a classification problem into a prediction problem. When you say prediction, are you talking about how you predict something in the future, or you're talking about, because I think when we talk about prediction, I often use it in linear regression. You're trying to predict.
Yes, something along the lines of linear regression. Yeah. Right.
Okay. Yeah. So, we don't really cover all of these things. Neural networks. I mentioned right at the start that they can do regression as well. SVMs, they can do regression. I think it would take a whole other session to show how they do that.
That makes sense.
Okay. So yeah, this is deep learning really. Right. So back to convolutional neural networks. And we're talking about image classification. So, we can think of, I think that really hot topic at the start of the COVID pandemic was, if you've had a chance to explore around Kaggle, since about April last year, there were CT scans, chest scans of people which had a normal chest scan, those that had pneumonia, and those that had COVID-19. And there was a lot of work there to see if you could train a classifier to tell the difference between normal pneumonia and COVID-19, because this is before this point, we weren't ramping up testing on a million scale. So we were thinking of ideas to do this. And convolutional neural networks was at the forefront of that effort. And so computer image classification. And this is a deep network. We want to try and classify simple objects. So at the end here, we've got our outputs. Depending on the value, we will call it whatever object it is. And it's just slightly different. So in neural networks, we would just input in vectors. So remember we had, I think Marcos had a slide where it was like X1, X2, X3, which are just our features. Think of CSV files, columns of data. But here, the space is different. This is pixels, or a large matrix. And so the idea about convolutional neural networks is we want to, right at the start of this network, it goes very deep, right at the start of this network, we just want to teach a classifier, like really basic things like boundaries. So we can see like, we've got the sky here and the sea there. These neural networks, it's like they're just like a newborn baby. They don't know anything. You need to teach them things from the ground up. So the idea is that early on in our convolutional neural network, we're teaching it really simple things like boundaries, different colors, curves. Okay, and as you go through the network, then you start to teach you things like textures. It might understand what shadows are, highlights are, things like this. And as you keep going through the network, it should, maybe pick up things like it knows the difference between an eye, because it knows eyes are round, if you look at the boundary of an eye, compared to maybe, the hull of a boat. So you start to build it from scratch, just teaching it pixel by pixel. If you have a cluster of pixels, it can say, oh, actually, this cluster here, this super pixel, contains just a straight line or even a curved line. So things like this, and yeah, so you just build it from the ground up, and over time you'll hopefully find that it can do things like classify the difference between a dog and a cat. Whereas right here, early on the network, you might only know the difference between a straight line and a curved line. Okay. So yeah, how do we do this? Convolution. So what is convolution? We're talking about matrices. So again, these are all matrices. An image is a matrix, or we saw in the clustering lab how we represent images in R. It was just a 3x3 array, a 3x3x3 array. Sorry, because it's a red, green, and blue channel, and you can even have a fourth array, which is the alpha channel. So neural networks, especially in convolution neurons, we're just dealing with matrices and images and so on. So when we say we convolve something, if we have our original image here, which is just in grayscale, so obviously the higher the color, the lighter the pixel is. What we could do is we use a kernel, so a convolution kernel, which we hope is going to transform this image in some way that makes it more digestible for our neural network. And when we say we convolve this matrix with this matrix, what we are doing is we have a sliding window. So if this is our convolution kernel, which is 3x3, we start off in the top left corner, and it's really simple. We just multiply. So if I've overlaid this on top of that, we've got 1 here and 3 here. We just multiply them together. So that, that's all we're doing. So the next value, they're both 0. 1 and -1. There you go. So just for this first position, we can compute all these and we end up with a new matrix. And then we take the final value. So we just sum these values up. So we end up with a new image or padded image. It's not going to be, so it's going to be because it's the product of, sorry, I'm just getting loads of emails on Canvas. Because it's the product of these two matrices, it's a smaller matrix overall. But just by doing this one operation, this convolution operation, we end up with this value of -5, which we slot in here. And then we're going to shift the window over and do all those calculations again, and we end up with -4. So we start filling in this new matrix on the right-hand side, which is our convolved image. As you say, we just keep sliding this over. We do the calculations until we end up with a fully convolved image. So convolution is just matrix multiplication. And I know at this point you might be thinking, well, how is this more useful than this? And it's not at this stage. This is just, just to demonstrate how you convolve two matrices together. However, there are certain kernels designed to do certain jobs. So, you may have heard, especially if you're a bit of a Photoshop aficionado, you may have, if you go in the filters category, you may have seen things like Sobel filters, I can't remember the name now, doesn't really matter, Sobel filters, so edge detectors, basically. So in this case, this particular kernel, I believe, is a Sobel filter, and it's designed to pick up edges in an image. So clearly we have an edge here, and what we do using our Sobel filter, we convolve these two together, and we end up with this. And so we know that the values here show that there's clearly an edge in here. And I'll just so I've actually got this open. So this is a really nice demo of different types of convolution kernels you can use. Again, it should be really similar to how you do things on Photoshop. But yeah, this is just showing the convolved value, and this is our kernel that we're using. We can choose different kinds of ones. So actually, let's just pull out a Sobel filter. Here we go. So we have an image here. And what we're saying is that this image of this person, the neural network just can't make heads or tails of this. It's just too complicated. So it's going to break the problem down into, can I take an image and just find edges? So it understands things like, so just this guy's face here. So, there's quite a lot of variation in the pixel values here, it would just overload the neural network. It's too much. However, when you take a Sobel filter, actually, my mouse it's a bit weird. The Sobel filter, if you look on the right-hand side image now, it becomes a lot clearer. It's more of a hard boundary. So, what we're doing, we can explain another kernel perhaps. Yeah, let's do top Sobel. So there you go. So can you see the difference between these two things? So, this kernel is set in stone. It's this is a right Sobel filter. With the left Sobel filter, we just reverse them, and so on. So these are nice little tools. These are things that the neural network can use. Hi there. Yes.
The matrix you showed us on the slide was 1, 1, 1, but in the Sobel feature is saying 1, 2, 1 itself.
Yeah, you can mess about with these values slightly. I think the main take home is that in a Sobel filter, an edge detector, the values in the middle are always 0, and then you can specify how hard you want to define your boundary in the convolved image with these values outside it. Yeah, so just to make that a bit clearer.
Thank you.
Yeah, so what we're doing is our neural network, this is more digestible. This image on the right is far more digestible to learn patterns in the image than it is with the original image of this guy here. And what we typically say, as you'll see in TensorFlow, there are hundreds of these different types of kernels. They all do something slightly different. And in TensorFlow, you can just say, just use 64 random convolution kernels. And for every pixel in the image, just in one layer, run all of these kernels over the top. So we're kind of chewing up this image. It doesn't mean much to us. I mean, if I just gave you this image of this man here, it's a bit like, maybe if you've seen the films, you go to see a psychiatrist, like, what is this an image of? These don't really mean too much to us. And I think this is where the black box argument again comes in, because if you were to peek inside what the neural network is learning off, and you looked at, he's like, well, what are these images? So they don't, so this, I don't trust it. It's gobbledygook. So I think you can kind of see how these things slip into a black box label. So that's convolution, and we use a range of these filters. This is a nice edge detector here. We use a range of these filters just to teach a neural network simple things like straight lines, curved lines, as you go through the network, textures, shadows, highlights, and so on. So you learn all these things. You've got to learn to walk before you run. You learn all these things before you learn the difference between like a cat and a dog, or something like that. Cats have pointy ears. So like if you see pixels in the image, if the neural network sees pixels in the image, we've just got straight lines in there next to each other, you think, oh, maybe it's a cat then, whereas dogs tend to have rounder ears. So this is how it works. We build it from the ground up. It's like teaching a baby, really, just teaching the simple things. Oh, why did it do that? Oh, sorry, let me just, yeah. Hi there, so it was the question.
Yeah, how well would the network deal with like slight rotations in an image? Or would it not?
So when you say rotations, can you just elaborate?
Well, say if you had a face, like normally, like that face was just normal, sort of straight, but if you tilted your head, or if like the face was upside down, would
would it
still struggle with that?
No, so what we do actually, I've got a set notebook on the go, which I'm trying to demonstrate this. Come aside, here we go. So what we do actually is we can do things like shear the image. So, when we're doing these convolution kernels, we are altering the image. And you're thinking, well, is it classifying the original image, or is it classifying some really horrible chewed up image, which is sent through a load of kernels? Another kernel that you can do is you can rotate the image slightly. So, or all the way around. So just as you might do an edge detector, we can input parameters into TensorFlow where you shear the image in a certain angle. So it tries to learn variance across images. So as you were saying, if someone was tilting their head slightly, we don't want to teach a convolutional neural network, CNN, just to learn how to detect faces where they're looking at you straight on. We will shear the image, manipulate the image in such a way that we learn variance as well in how things are detected. So, does that help?
Yeah,
interesting. Yeah, good stuff. Yeah, so there's parameters to do this in TensorFlow, and you can see all that.
Sorry, Aaron, is there a particular way it works in video?
Is there a what? Sorry.
Like, does it work differently on videos? Like pictures.
Yeah. So videos, it doesn't work differently. Obviously, you're just feeding in a data stream instead of just a single image. So yeah, there was NHS Digital Conference about 6 months ago. This guy, I can't remember his name, Gary something. He basically built a convolutional neural network to look at CCTV. They didn't put it in practice, by the way. They just demonstrated that you could do it. That you could take CCTV image of high streets and detect when people weren't wearing a mask. I mean, they've not put it into practice, and they never would, because that would be spying on people and so on. But it's just to demonstrate what you can do with video image. So yes, you can do that. For example, I've seen ones which they're looking at traffic lights, CCTV with traffic light, and it will detect when the light's gone green. I think that's a bit overkill because you can do that with simple, we looked at cluster analysis yesterday, looking at RGB values. So yeah, you can do it on video, and it doesn't have to be this. You need a powerful machine to do it, to handle the stream of data, but yeah. Okay, yeah, so just, so this star or asterisk, sorry, that we've been looking at, this is called the convolution operator, So hopefully now, if you hear the word convolve or convolution, we think of the word convoluted as being a convoluted process. That's complicated. Convolution is simple. It's just matrix multiplication. We just slide this kernel across our image and end up with a result. So yeah, in this case, and yeah, good point. So I put values of 1 and -1. If you mess about with these values on the outside, what you're doing is I'm specifying how sensitive the edge detector is. So this is a Sobel kernel. There are many. I think in the notebook we'll probably just ask it to give us 64 random different kernels, and so on. So one thing to talk about is pooling. So you see this again often when you're defining your layers in TensorFlow. And yeah, pooling is, you might have an image like this. This is our convolved image. Okay, so we've got our raw image. We've convolved it with whatever filter it was. I think it's saying stride filter. I don't know, whatever. And we could pool our data. So we've got these pixels here. So this is 4 by 4. So the more pixels you have, the more data you have to process. And we could pool it like this. So we just notice that in the top left, these are all a certain value. They have a range, but they have the same color, and we just pool it like this. So you see this a lot, after in convolutional neural networks, after a convolutional layer, you might see this pooling layer afterwards, and it's just to help reduce the number of features as you go through the network and keep it running quickly. Obviously, you must accept that it does introduce some noise or error when you do this, but yeah, they do get used a lot. Okay, so hopefully you can see that. Yeah, we got these images here. Is it dog, cat, boat, or bird, or so on? How it goes through the network. In this layer here, in the convolution layer, will chew up the image. So I think what this is trying to represent is that the layers behind this, there's 3. They're all its own kernel. So we chew up our image, we make it more digestible. So we learn, edges, textures, different colors, and so on. Here's some pooling. So again, we've done a lot of processing here. There's a lot of information to carry through. So we'll pool this, and we just keep adding these layers in as we go along. So that's the unique thing about convolutional neural networks compared to any other network is this idea of convolving our image with certain kernels. So yeah, I've had quite a few questions about R and Python, which is fair enough. When you're learning what you need to do, what do I need to do to get employed, and things like this. Can we do deep learning in R? And the answer is yes, we can definitely do deep learning in R. It's a bit weird. So I've said TensorFlow a few times. TensorFlow was the machine learning framework designed by the Google Brain team, and it was a specific framework just for deep learning neural networks. So after the ReLU function came out and deep learning was back on the cards, so Google within a couple of years had developed their own Python library called TensorFlow, and they open sourced it in 2015. So this is where R comes in. So, before they had open sourced this, I think actually there was an implementation of PyTorch and Theano for R, which are other frameworks. But we're going to be looking at TensorFlow today. And when I say the word tensor, or the way Google defines the word tensor, they're just saying a very big matrix. So a tensor is a very big matrix. These matrices, large matrices, are flowing through a network, and So that's where it gets the name from. So in R, a lot of people actually they use this. It's kind of like an API, if you like, to various backends. So something called Keras. So Keras is in R or Python, and Keras, just if you're not familiar, with APIs, it provides some nice functions, a bit like in tidyverse or dplyr, you have things like you chain verbs together, like summarize, group by, gather, things like this. Well, Keras is kind of like the equivalent of that. It is an API call to TensorFlow, if you want to think of it like that. TensorFlow is the back end. Keras is the front end, where we have our nice predefined functions. We just call them in R, so we don't have to do loads of programming to make TensorFlow work. And Keras, it doesn't just provide a front end to TensorFlow. There are others, older ones, so Theano, PyTorch, and things like that. So Keras can work with those. In R, when you install the Keras package, there's a function called install_Keras, and what it does is it installs. Blink and you'll miss it, but it installs using the Reticulate package a Python virtual environment. So when we're doing deep learning in R currently in 2021, we're actually just installing Python on a system, a mini install using Miniconda or something like that, just to get the TensorFlow backend, the libraries. And we use the R Keras library to interact with that. So when people say they're doing deep learning in R, what they really mean what's the date today? The 12th of March, 2021. When we're doing deep learning in R, especially using TensorFlow, we're wrapping some R code around Python. So people are asking, do I use R or Python in machine learning, deep learning especially? What you'll find on Kaggle, if you just go on various data sets, the hot data sets, the competition data sets, most of the notebooks are in Python. And I think it just comes from this legacy of Google developing TensorFlow and PyTorch already existing. But you do get the odd R kernel. The code's actually quite similar. So yeah, you definitely can do deep learning in R. There is talks actually of a native deep learning R environment, so a TensorFlow for R, but I still don't see that appearing in the next year or so. Both Marcos and I have talked about GPUs, and you might be wondering why we talked about GPUs. You obviously know we got a CPU on our computers. So GPUs, or graphical processing units, they're a staple of deep learning. So these help speed when we train our models, they help speed that process up. So all through this course, we've been using just even on Kaggle, just CPUs, or if you have been doing it in RStudio, it's like you've just been using a CPU. However, GPUs, they work really well for deep neural networks, and neural networks for that matter as well. So GPUs, they've been knocking about for years. If anyone's been into gaming, the Alienware laptops and so on, even back in the 80s. GPUs, what they are designed to do is to take pixel data. So we get binary data from our CPU, ones and zeros. And if we want to, watch a program, TV program, the job of the GPU is to make sure all the pixels are the right values and where they should be. And basically, what this means is matrix multiplication. So GPUs, and you often hear things like frame rate. GPUs, all they're doing is they're taking care of this process of, giving us a sorted noise. If we don't sort the white noise out into something, it won't be an image. So they take care of this process, millions of matrices together, 60 times a second. That's my frame rate is 60 times per second or so on. And, neural networks, especially in CNNs, as we've seen, we're doing the same thing. If we're using in our first layer of a convolutional neural network, so we have this image here, which is just a matrix, or as Google would say, is a tensor. if we have 64 different kernels we're using, there's 64 different times you've got to chew this image up, multiplying things together. Think of all the how you're convolving every pixel with a convolution kernel. So there's all this matrix multiplication going on. And so GPUs, they get used a lot. They were designed to handle matrix multiplication. So it's quite clear how they work well with neural networks. And this is one reason why I think Kaggle is superb for deep learning. Anything I've learned in deep learning has always come from studying other people's notebooks in Kaggle. And the best thing, I think, is that you get some free GPU or even TPU, which I've not actually used TPUs. Hopefully I'll get a chance to explore that. But, in a Kaggle notebook, and you can only have this on doing one notebook at a time. You can't have parallel notebooks. There's an option to select an accelerator, and you can just select GPU or TPU if you have it as well. So we're going to show this in the notebook. And you get, I think you get 46 hours free a week of GPU time. So, if my neural network takes an hour to train with GPU, then I can do that 46 times throughout the week. And what I tend to know, I do more work with RNNs than I do with CNNs. But what I tend to find is that GPUs, they will speed up the training process by, somewhere between 10 and 15 times. So, they're a staple. If you want to do deep learning, you need GPU. Very quickly, I'm hoping to demonstrate. I've got a problematic second notebook, which I've been trying to fix as I've keeping an eye on it. I've been trying to lecture these slides. Hopefully, we'll get to look at transfer learning. If not, I've got the code there. The issue I have is that the newer versions of the TensorFlow backend, they don't play well with pre-trained models on Keras with a previous version of TensorFlow. So I'm trying to fix that issue now. But anyway, let's just briefly talk about transfer learning. So clearly, training, the fact that we're having to delve into GPUs gives you a clue into the time it takes to train these models, the processing power it takes to train these models. And if you were to train every single model from scratch, that is problematic. So the first reason it's problematic is because obviously it takes time. The second reason, and this is especially so in healthcare, because access to medical records, X-rays, and so on, because it's patient data, there's this consideration that access is difficult to come by because you have to be a trusted party. Where we are in the Sale Data Bank, although we have anonymized patient data, we certainly don't store clinic letters in Sale because they have people's names. Similarly with images as well. I don't know if you've got a funny piercing or so on, you can potentially identify someone. So, gathering a lot of healthcare data like this X-ray classification problem here, that can be problematic too. So, what a lot of people tend to do is this thing called transfer learning, and there's a nice website called ImageNet, and this is where you find all the pictures of cats and dogs on the internet just end up in this website. And what people do is they will just write deep neural networks, which they will optimize these over like a number of weeks, even months, until they get to a really nice deep neural network, which can tell the difference between a cat and a dog. And what you can do is you can say, we were talking about the whole idea behind neural networks, and deep learning is included, is to optimize the weights. So you start off, it goes through this neural network, deep network, thousands, millions of times, whatever it is. And at the end of it, we'll have some stable weights, where the weights are giving us accurate classification of whether it's a cat or a dog. You can save these weights. This is the issue I'm having on my notebook. You can save these weights in database or a HD5 object, which is what TensorFlow uses. And you can import these weights into a model or a deep learning framework, which is interested in maybe, detecting cancer, not cancer from a scan. And you think this is crazy because this deep neural network was trained to understand the difference between cats and dogs. What we don't want to do is put in an image of someone who has cancer and say the diagnosis is you're a cat. that's something we definitely don't want to do. So what we do in transfer learning is when I was saying right at the start of a convolutional neural network, a lot of the work is focused on learning the different things like what's a straight line, textures, highlights, shadows. These are all things which will appear, they'll be relevant. How many ears you have is not relevant to this problem, but things like textures, shadows, shadows on a CT scan, that's what you're looking for things like cancer, pneumonia, and so on. So the early stages of a deep neural network like this, they're really useful for plugging in what you've learned at the early stage of this network into this network. So what you can do is you can specify the number of layers into your network. So this is our fully trained network that tells the difference between cats and dogs. And we can say, I want to save the weights just from maybe the first 3 layers of this network. And, where you're thinking, okay, by this point, you should know what textures are, what highlights and shadows are, and things like that, and everything before that. So we can insert these weights, or these layers, if you like, into this neural network. And what we do is we use the images, our training data, which is these images. There's a gold dust. To get hold of these images, you have to go through so many governance things, rightly so, for patient privacy. So you just use these images to fine tune. So we have our computer, which is not a baby anymore. They're like a toddler or something like that. They can speak and all this kind of stuff. And then you just fine tune it with the actual problem you're interested in. So transfer learning is a good staple. And this ImageNet website, people will just, I don't know if there's people in their own time. I mean, who's doing this problem? I don't know. Obviously I work in healthcare. I don't know who's doing this in their job, but people will train deep neural networks to solve this problem. They'll save the weights, and it's just a one-time thing. Once they've done it, that's fine. They may have taken a couple of weeks or months just to do this. Your GPU's chugging away, and they save these weights, and people can just go and use these weights for whatever they want to do. And I'm really hoping this notebook issue I've got will allow me to demonstrate that. If not, I can at least just show you the code to do it. So that's transfer learning, and this happens a lot in deep learning, in CNNs. I think unless you've got huge amounts of data of the specific problem that you have, quite often you're looking at using transfer learning.
So Aaron,
yes.
One question, so you mean to say that in neural networks, deep learning, you always use labeled data? You can't go with non-labeled data?
So you mean unsupervised? You're talking about unsupervised learning? Okay.
So further, this neural network is further divided into unsupervised. There we do without labeling.
Yeah, so you can get implementations of unsupervised learning. A take-home message of this week is that all of these fancy techniques, you can use them for regression, supervised or unsupervised. They all have various different modes. What I'm presenting through the week is what the common things are. When people use neural networks and CNNs, they're usually doing this for supervised learning, but you can do it for unsupervised.
Okay, thanks.
So I think we'll look to take a break now. We'll take our half-hour coffee break, but with any questions before we do that?
That's a quick question on ReLU. I think it's just I misunderstood at the time. With the other activation function, I think they were normalized. We say in ReLU isn't normalized, and if not, does that cause any sort of problems, or does there any disadvantages to that where you get gains in the backflow?
So when you say the activation function is normalized, what do you mean there?
Oh, I don't know. I might be completely misheard lots of things and asked a nonsense question. I just wasn't sure if ReLU affected normalization, basically.
So one thing you saw, I think what you're trying to get at here is you normalize the input.
Right.
Of the neural network, and you always do that with the neural network. Again, we looked at cluster analysis yesterday as well, and you tend to do that as well. If you don't normalize your things. You get skewed data. You have to look at things like the Mahana labelis distance and all that sort of stuff. So the same thing for neural networks. So ReLU isn't affected anyway by how you normalize your data.
Cool. Yeah, I was just mixing things up. Cool.
Yeah. No worries. Okay. Any other questions? Or you're all okay?
So one question, why does training with cats and dogs first would give us better results in terms of the cancerous or non-cancerous? Wouldn't it just not be better to just use those images to begin with, the cancer and not cancer?
Yeah, so there's a few considerations there. It would be better if you could just train a model, and my recommendation is if you do have enough data to train a neural network on just the problem set, you should definitely do that. Don't go looking for cats and dogs to help you out. If you have the data to get good accuracy, go and do it. So that's the first thing. The other thing consideration is speed. Like honestly, when you're in a deep learning land, these things to get a well optimized model, they can take months, and you need access to I'm thinking of Tesla's gigafactories now. You need months of GPU access to GPU servers. Think how many times Marcos was showing the loss output. So you have the loss in the training set versus the test set, and how long that can take to converge. It can just take ages to train these things, and sometimes you might not have the luxury of doing that. You don't have the GPU server setup. I mean, if you're doing this in NHS, you definitely won't. You just don't have the money for that kind of thing. So, best case scenario, yeah, definitely just use the data from the actual problem you're interested in. But if you can't do that for those reasons I've just underlined, you are looking at some transfer learning, and you still get good results. People demonstrate you get really good results with this. And the reason, as I said, why you can get away with using these images is that, you don't use the entire network, the weights on the entire network. You only use the weights at the beginning. So what you're doing is you're just inserting the knowledge of a deep learning network that has only learned things like straight lines, text, shifts, shears, and so on, things like that. So you often find transfer learning gives you just as good results. But yeah, I take your point. Just depends what scenario you're in. You have to choose appropriately.
Yeah, thank you.
Okay. So I make it just coming up to 20 to 11. So we'll return at 10 past 11, which will hopefully give me time to fix my second notebook. Okay. So I'll see you at 10 past 11.
See you.
Okay, yeah. So I've got these two notebooks up, and this one is just at the end. It takes about 15 minutes to train, and I run it about 15 minutes ago. So I'm expecting this to pop out any minute now. But yeah, we'll go through our first notebook. There are two. One has an issue, but it is actually a simple issue to fix. I can't fix it in time for demoing it, but I will still go through the code. The important thing is just to show you things like this, how you build a model in Keras. So we have, this is our problem set. We're looking at cells that have been infected by malaria. So there's a parasite in the cell, and this is an infected cell, and this is a cell which is fine. And our setup, when we use Keras, what we are doing, let me just find the relevant cell. We're reading things from a directory instead. So, there are lots of functions in Keras to read things on directories. And here is our directory. We've got our training set. You see that these are loads of images. There are a lot of images. And we've got a test set, and we've just got things you can do a single prediction on. So that's some output in here. So let's just talk about how you get Keras and TensorFlow set up. So actually, it's best practice just to install Keras first. When you load the library for Keras, there's a function called install Keras in here. What this is doing is installing Python on your computer or in this notebook. And so if anyone's used Python, it's just creating a virtual env for you called R-Reticulate. So the reticulate package in R, which Keras loads for you, helps you run Python code within an R environment. So that's the first thing to notice. When you're using Keras and you say install Keras, this function is installing TensorFlow. You can install different versions of TensorFlow. I'll tell you more about that in the other notebook, which is where the issues arise in. And yeah, and then you can load this library TensorFlow as well. So yeah, there are a lot of packages in here. Don't worry too much about them, and don't worry too much about this cell. This is just to show you the images down here. It's just a bit of code to do that. So I'm pulling out the images from, I think, just the second image on the training set. Yeah. But don't worry too much about this cell. It's nothing to do with Keras. I'm just showing you the images. Again, this cell, don't worry about it. What I really wanted to show you was this. So this is typical code within Keras, and this is how we're going to find our CNN. So we load in our model and we're just adding in layers. So some things will look familiar to you. So activation ReLU. So we're using ReLU units. So we're putting in our first layer here. Filters. So these are kernels. So what I'm saying is just use 32 random convolution kernels to run within this layer. So you'll end up with 32 versions of each image. You know, in the training set, this many images go through, and each time one image goes in, you've generated 32 different images just in this layer, which have had a different convolution kernel applied to them. And you can set the kernel size as well. So you know, there's lots of parameters you can mess about with. Obviously, the smaller the kernel size, this is the smallest you could use. That would be useful. The longer it takes to run. And you've got a pooling layer. So I mentioned that after we've chewed up all of our images with our various different filters, our kernels, you know, that's a lot of information to process and send through the network. So we do pooling just to try and aggregate our images as we go through the network. And again, if you just want to add a new layer, you know, we just pass these things in, and the Keras library, by the way, was optimized to run in conjunction with dplyr. So we just, it looks super simple, you know. So here's a model I want to run. Here's a layer, and I just keep piping layers into layers like this. So actually this code, all it's doing is just adding, you know, 64 kernels instead. And we just keep doing this. So the code, even though like everything we're talking about deep learning neural networks, we had a question, I think it was from Shashida earlier. You know, Marcos went through an implementation of neural networks yesterday where he programmed it up from scratch. And that's purely for demonstration, just so you can go through each line of the code and see what it's doing. You know, in practice, you would never, you know, I certainly never do that. I think, you know, a lot of people, especially just for research purposes, to test if something's feasible, you know, you would either use Carrot, you can call a neural network within Carrot, as we did with SVM linear. You know, here's the code. And, you know, these functions, they're making a call to the TensorFlow backend, where obviously there was a lot of code there just to implement TensorFlow. But you certainly, you're not doing anything from scratch here. Once you are happy with a model, however, as Marcos briefly mentioned yesterday, if you want to put it into production and you need it to run really fast, that's when you have to start thinking about coding up this model in a language like C, or Julia is another language which is basically just sits on top, almost at the same level as C on your computers. So Julia is kind of another language in data science, which is designed to be ripping fast. It's still not got the community there yet, but you know, you can still do it. So this, just if you just look at it, the code is pretty easy to understand. You know, if you can run Carrot, you can
So
run
Aaron,
this.
Aaron, one question, like
Yes.
you said that we need to convert it into C. Are there any, like say, any websites or any tools where we can put this code and we can get an output of C language rather than I writing it entire thing? Is it an option there, or we have to code it entirely into C language?
Yeah, you'd have to code it yourself, and I have the luxury of not being in the position to have to do that, because I'm in university. But yeah, you would have to code it up yourself, and I don't know what types of people these are that would be putting these things into production. I don't know if they're just C developers, all-purpose C developers, or I'm sure there are people which they have a machine learning background and enjoy building models that you put into production. But yeah, it's certainly not an area which I have to deal with. Being in academia, you just prove a concept works, so I can just use Carrot or Keras or whatever. I can say, yeah, look, it works. It does a good job. Code this up to do it really fast. If you need to do that, there's a question for what video can you do CNNs for video? You would almost certainly be, you're handling a data stream. You'd almost certainly be coding that up in something beyond Python or R. So the argument of Python versus R, which I think that even goes out the water when you have to start doing stuff like that. Okay, so another question there.
Is there a reason why is it like the third layer doesn't have an input shape or activation, or is it because their default that but your mouse is there?
Here.
Yeah.
Yes, I think this is actually redundant.
It's probably default, is it?
Yeah, so I can double check that. But yeah, I think this just default. Again, I probably don't have to put this in. There'll be a default activation function. I'm sure it's Relu, because we're talking about deep learning. I think that this is Jelu. You could do that, but
cool.
I'll put that, drop that in actually.
Aaron, a quick question.
Hi there.
So in each layer that's displayed here, you are doing everything from convolution to the fully connected part over and over, right? So that's happening 4 times for each layer. Sorry,
Yep.
I mean, that's happening 4 times in each layer.
Yep.
Okay.
There's a few things at the end just want to talk about. I think you're all okay with what happens in a convolution layer, and I think you're all okay with what happens in a pooling layer. So yeah, flatten. So I think we kind of spoke a little bit about a similar idea in our cluster analysis notebook yesterday. So do you remember we were having to convert our array, our raw image data, into a data frame so we can actually do some nice operations on the data frame? A lot of the deep learning libraries and stuff like this, they work on data frames. They don't work on arrays. So things like, doing operations like decision boundaries, neural networks, they do operations on decision boundaries. What they don't want to be doing is to be ingesting an image or a matrix or a tensor. Think of these as tensors. To actually do some operations on this, they would flatten the layer just into a vector. So that's what this flatten layer is doing. And this dense layer. So what you find in deep learning layers is it can be quite computationally expensive to what is there a comma there? There you go. To connect all the neurons of each layer to all the neurons of every other layer going forward. So what you find is that you will just randomly not assign some neurons to each other between layers. But right at the end, when you want to take advantage of everything that neurons learned, you can create a dense layer. So this will just reconnect all the neurons right at the end. So all of these will be connected to each other. And the third thing is this layer dropout. So, we looked at the parameter tuning. rock curves and crossfall validation lab. So, you know, when you run Carrot, you were doing grid search, and in grid search, you can just test different values of the cost parameter C, or, you know, N tree, M trie, and so on. And with crossfall validation, you would run it on 10 different folds, perhaps. So you end up with, like, you know, running SVM 56 times. You know, that's really not feasible to do in deep learning. You know, it takes long enough just to find the optimum weights. You know, going through all these epochs, going backwards and forwards to the network, that can take ages. So really, it's kind of not feasible in that sense to do things like crossfall validation with deep learning. And so you might think this is a problem, because I kind of sold you that crossfall validation, things like that, are a good idea to get model stability. So, you know, how can we approximate this in deep neural networks, and even just neural networks? And the way to do this is, instead of having lots of different folds of data and then putting those to the model, you randomly turn neurons off. So as you go through the model, the network forwards and then backwards, the next time you do it, you just randomly switch off some neurons. And this is kind of like to simulate random data sets. So, you know, Marcos was saying yesterday that all of the outputs from a neuron, you can think of them as features of your data set. Your data goes in, it goes into a neuron, and it comes out, and the value of that neuron it comes from the original data multiplied by the activation function. And so you can just think of anything which comes out of a neuron, just think of it as an operation applied to your original data, your features. And so if we just randomly switch off some neurons, this is kind of like bagging, you know, where you would, like, in random forest, where you send one data set down a tree and you send a different randomly sampled data set down another tree. You know, by dropping out certain neurons, you're effectively kind of aiming to replicate that process. So it's saying, as you go forward through the network, the next time I want you just to turn off different neurons randomly. So there are lots of different options that you can do when you run this network, and these are some of the, you know, just the common ones. And I adapted this notebook from an existing notebook. As I said, the way I've learned deep learning entirely through Kaggle is just to look at other people's notebooks and adapt them to problems I'm interested in. You'll see that in the RNN later, where, you know, we actually use a problem that me personally I'm interested in, what I do in my research.
How do we deactivate individual neurons in this? Because I can only see layers here. I'm not sure.
Yeah, you would never want to manually deactivate neurons yourself, because if you think of it this way, there's loads of neurons in the deep in the network. There's no way you would know what's a relevant individual neuron to switch off. It I suppose is a bit like saying, you know, in random forest, where I wanted to do the bagging, send down a different tree, is a bit like saying I want to actually, go ahead and bag some data, but don't include this one row of data for some reason. You know, in here, that's even more convoluted, because I think it's this black box thing again. You know, although we understand what's going on in each individual neuron, when you multiply the contributions of all the previous neurons into the next layer, you have no idea what each individual neuron is doing. It's only when you combine them at the end, when you get to this stage, we start to flatten things and reconnect all the neurons together, that you have an idea what's going on. So this layer dropout, it will randomly drop neurons for you. I don't really see any sort of sense in you manually deciding to drop a neuron. If that makes sense.
Yeah, that makes sense.
Okay, so has it run? It's still going, bugger. Okay, yeah, so, you know, this is how you would set your model up. Is the GPU switched on? It is. So by the way, you know, if you want to use GPU, you can just switch it on. It is on. I don't know why it's taking too long, but anyway, so we've got our model, we just defined it, and then we compile it. So Marcos talked about loss functions. To be honest, I don't really delve into these things. So this is a default one, which a lot of people use, binary cross entropy. There are different versions you can use. Marcos is clearly the enthusiast about neural networks. He paid me to do the lecture. No, I'm just joking. He didn't pay me to do this lecture, but he clearly loves these. So if you want to know more about different loss functions, Marcos, I'm sure will be happy to explain if you email him. Yeah, cancel, go away. So you can print our model. We've compiled it. We're telling it which loss function to use. Metrics accuracy. You could put in sensitivity if you wanted to. And I would actually recommend that usually, because if you're looking for disease, that's what you want to do. And it's just a nice summary of your model. And you can see how the parameters scale up. So I think this is where we use 64 kernels. So you can kind of see that there. And so a lot of this code you'll see in any notebook in Kaggle. It's just, people just copy these all the time. And this is true for this cell here as well. So Keras has got a nice function called flow images from directory. And all you do is just you defined which is your training directory, which is, where did I define it? Here. Just copy the file path and put it in. And what it does, it just reads in all the files from the directory for you. You can set things like understanding that because it's binary, because we've got, if we look at our test set, there's two. This is a binary classification problem. So Keras, they've clearly thought about how you read in data. You're not just writing a for loop to read in images from your directory. So this is all optimized. So this cell and this cell, these are really common to most notebooks that are using Keras. So, it's fine. So the thing, I was hoping this would run. At the end, we get our training loss versus our test loss. And that's all I wanted to show you was the output of that. But you can see how you can set this up. So there's a few things. We've got our model. Maybe this will run by the time I go through the other notebook. We've got our model. We put into a function called fit generator, which is going to actually fit. This is where we do our training. And we can set things like number of epochs. So, how many times you go through the network. Steps per epoch, it escapes me. I forget what this does. But we can put in our training data. We can put in our test data. So that's how you get your training loss and your test loss through there. One thing I would recommend is when you're doing deep learning like this, so this is going on about 25 minutes now. I have a sneaking suspicion I run it without the GPU on, but you can record how much time it takes to run your model. And I would always recommend doing this. There's even code like library mailer. You can send yourself an email when it's done. So there'll be a function you can call in here, just say, it's done now. And, when you see people publishing papers in this area, there's two things that they absolutely love to report other than the accuracy of their model. The first is what GPU card they use, what server they use. They just absolutely love describing what they run it on and how long it took to actually run their model. So people that use deep learning, they get really enthusiastic about describe. It's like I play guitar and I could talk about all my guitar pedals to anyone. It's like people that do deep learning, they will talk to you on end about their GPU server and how long it takes to run their models. And you'd be surprised how long it does take to run these things. The architecture that some of these people have and how long it takes just to train like something to learn what a cat is or a dog is from ImageNet. It takes ages. I was really hoping this, I had it earlier. I think what I've done is I've just run it without the GPU. And as I said, it takes about 15 times as long. With a GPU, this takes about 10 minutes, 10, 15 minutes. So I think that's what I've done. The problem is that you can't have GPU. I've got 46 hours of GPU free per week. You can't have it running concurrently on two different notebooks. And I think what I was doing was trying to fix two notebooks at the same time. and I pinch the GPU away from this notebook onto this one. So yeah, second problem, which I know what the error is here. This, about 6 months ago, this run fine, but clearly TensorFlow is updated, and I'll describe what the issue is as we go further down. But it's a similar thing. You know, we're looking at chest X-ray pneumonia versus people who don't have pneumonia. Again, we've got this nice structure, as we did before. So we can see that there, you know, the read-in. Find it. Is it? Oh yeah, here. There we go. See, remember this cell. Really simple. You can put extra parameters in to give it explicit information, and so on. So again, similar setup. If you're doing this on Kaggle, you only need to run this once. By the way, you don't need to reinstall TensorFlow each time. So the issue here is that when you do this, it installs the latest version of TensorFlow. And what I'm doing, I was trying to demonstrate some transfer learning. So these are pre-saved models that Kaggle offer you. So there's a you can just add data, type this in, and they say it's got the pre-trained models. These models, they were trained on an older version of Keras and TensorFlow, and there's an issue using these, inserting these into the newest version of TensorFlow. That annoys me incredibly, that you don't get this backwards compatibility, and I'm sure it annoys you more that you're not seeing me demonstrate this notebook properly. So I apologize again. I am also very annoyed, but I'll go through the code anyway. You can take these two notebooks away and play about with them to your heart's content. You know, all these notebooks for the week, you can just take them home with you. I'll explain the error, so which I will try to fix either to this evening or the weekend and update them. But anyway, same setup, define our training directories and so on. Someone asked about shifting faces. You know, if you tilt your head, if you grow a beard, how does the iPad know it's your face? You know, things like this. So there are options to do this. We can manipulate our data or augment our data in a certain way. So we've got this function called image data generator. It does simple things like it will normalize your inputs for you. So, you know, if you've got images that are slightly different sizes, it will just resize them all, rescale them. We can rotate our images in a certain way. We can shear them as well. So we can sort of stretch, have this effect of stretching pixels in a certain direction. We can flip images. So if you've got an upside down face, you can still, vertical flip. If you can set this to true, obviously, if you wanted to. So there's lots of parameters to actually manipulate our data in a certain way. And remember, this is okay. When we do validation, we're certainly not going to feed in images which we have manipulated to our heart's content and report accuracy on. We're just doing this for training purposes. Remember, the idea of a CNN is like, you know, we've got our baby CNN. It doesn't know anything. You need to teach it things like textures. You can see how these sort of things, combined with convolution kernels, it just teaches a CNN really basic things like what's a straight line, curved line, and so on. So yeah, you can absolutely synthetically generate variance in your training set so that you're hoping that the classifier doesn't get fooled by a test image with someone's like grown a beard or tilted their head or so on. Okay, and yeah, we've seen this kind of function before. Flow images from directory. I guarantee you in every Kaggle notebook, you will see this function. So here we've got train and test data, which is what we do our train and test us on. We've also got a validation generator because we've got a third directory called val. This is our completely independent test set. So remember, just to reiterate, even things in like cross-flow validation and so on, we typically have three different data sets. We have a test and a train. So they're used to optimize our model. So when I say optimize our model, we're talking about hyperparameter tuning, updating weights in the neural network. As Marco said, set the threshold on a ROC curve. All those are done in training. And then you reserve a completely separate independent test set, which is what you just accept all the values of the parameters that you've set during training. You just run it on the test set, still plot your ROC curve on the independent test set, because you can see exactly how it's done. So this is a typical setup in machine learning. If you don't have if you're limited by the amount of data you have, just stick to a simple train and test. But if you can do an additional 4 or 5 or 6 even different evaluation sets, then you should try and do that. Right, so let's explain the issue with this notebook. Maybe one of you, the main issue I have is that all the error codes that come back to me, they're all in Python, because I'm running this basically on Python. So it's a bit foreign to me, but I will explain what I think is the error, what I pinned it down to. This H5 file, it's a weird database format. These are pre-trained weights from the ImageNet website. There's different pre-trained models. You can try any of these. As I said, I've just imported this from Keras. Yeah, so the issue is that this was trained on an older version. So clearly, at some point between the TensorFlow versions, the way these H5 datasets have been constructed are slightly different, or the way they're ingested in TensorFlow are slightly different. This is where I get my error. And all I was trying to do was create a base, that I'm trying to reserve the first couple of layers of a pre-trained network. This is cats and dogs and things like that. Save it into some layers that I want to use. And what I wanted to do was just insert that in. So again, this is where I call my model. It's actually a really simple model. There's only one additional layer. This conv base, somewhere in here, there's a parameter where you can set exactly how many layers you want to borrow from the base. But anyway, you just insert this in. That's the first thing it does. This is cats and dogs, this layer. This was trained on cats and dogs and boats or whatever. But the idea is just to teach the model what textures and lines and things like that are. Then you put it into our actual data that we're using. So you put into layers. The idea is that we then place our chest X-rays in from here. So cats and dogs here. Then all the rest of these layers we're feeding in. We're dropping in our X-ray scans. So yeah, there's a few things. Relu I'm using here. You can mess about with different activations for softmax. So right at the end, you can have a soft boundary if you wanted to. Marcos was talking about the output node on neural networks. You can mess about with the activation functions. You can have a step function, which literally just reports the class boundary. Is it this or that? You can have softmax. This is another version of a sigmoid. It's really similar, and so on. So yeah, this error, I think you can solve this by basically in here specifying an older version of TensorFlow. So I was Googling this over the last couple of days because I noticed this error midweek, and this appears to be the problem. These pre-trained Kaggle weights, they don't work with later versions of TensorFlow. That really annoys me. But there we go. I just haven't got time to do it. But I'll try and do this on the weekend and fix it. And again, you can take this notebook away with you. So we compile the model as before. Oh yeah, sorry, this is really important. Remember these weights, these were trained by someone else and they did really well on cats and dogs. I don't want to retrain these. I don't want to overwrite the weights. Well, you could if you really wanted to. But if you do this, if you retrain the base, then that's going to take longer for your model to train. So I'm just keeping these fixed. I don't want to rewrite these weights. Okay, again, so we have our model, which we compile.
Sorry,
yes.
Aaron.
Hi.
You said that the base did well with cat and dogs. How did you know did well? How did you evaluate it for using it?
I'm putting blind trust in the fact that model pre-saved weights that make their way onto a central resource like Kaggle, which has been administered by people that are interested in this area. I'm just taking their word for the fact that the weights they've put up has done a good job. I suppose that you should go back and have a look where this model comes from. So I don't know if I just new tab. I think you can follow these links, and I'm sure you'll get to a point where the particular model I'm choosing, you can find out the exact specs and accuracy and how well it did. But I'm just blindly using this model. So that's my answer. I should go back and check really, but everyone does this on Kaggle. They just pick one of them, pick one of these pre-trained, try all of them and just see how well it does. There's a few other things. These aren't terribly important. There's a class imbalance. This is the main one. And so so here, when we put them into training, we just want to level out how many training samples and test samples go into our model. It's not amazingly important there. So this, remember, am I on the right kernel? Oh, this is me debugging, trying to find the error in this. So actually, we can remove this cell. This is me just trying to debug why this didn't work. So I'll remove this. Yeah, and then this again, model fit generator. This is where we do the training. You should probably wrap it up in something like this, so you know exactly how long it took you. And you would run that again. And make sure your GPU is turned on before you run this notebook. Otherwise, you end up in a situation where we're here and my model still hasn't run. Maybe it'll run by the end of the day. I'm really hoping, so I can at least show you the plot. But yeah, after you train a model, so there's a few things you can make predictions on the test set. It's a nice one called predict generator, and you just feed in the relevant directory. This is just changing columns on the resulting data frame. There's nothing fancy, and you can also do a ROC curve. So based on your predictions, we can still get our ROC curve there. So I really apologize that I couldn't run this notebook. I was foiled. This, I said this when I demonstrated this to the third years, because I teach machine learning in undergrad third year. This worked fine back in September. But clearly the version of TensorFlow is not agreeing with these pre-trained models at the moment. So I'll aim to fix this notebook over the weekend. So at least, after you finish this course, all is said and done, you can still take this notebook away with you and adapt it to problems which you may be interested in for your dissertation, perhaps. So yes, hi.
So every time TensorFlow updates, there could be a problem with the code.
Yeah, the issue, and I've highlighted it here, which I'm going to try and fix, maybe someone will fix it quicker than I do, is the latest version of TensorFlow, which is the default, when you install, use this function, it installs the latest version, which is 2.1.1 or whatever. As I was been Googling this throughout the week, a lot of people are pointing to the fact that the pre-trained models that come with Kaggle, the way they're ingested by the later versions of TensorFlow, it'll throw up the error that I was getting here. So people have just suggested manually go back to, I think it was version 1.8.0 TensorFlow, and you can manually specify this in here. Oh, I'm on an American keyboard. Like that. So I think, you know, just that's the thing I need to try now is just reinstall TensorFlow within this notebook with an older version and just retest. The one thing you can do, which in my state of panic on Wednesday night, is I removed the base. So I trained it from scratch. So just removing this line, you'll actually just train it from scratch. That took ages, like around about, like I started running that on Wednesday evening. Thursday around about midnight, it still hadn't converged, even when I was using GPU. So that, I think that demonstrates the problem of, or the benefit of using pre-trained models. Your thing will run a lot quicker. So yeah, I was in a bit of a state this week trying to get this notebook to work. But there you go. So were there any questions about, you know, how you would set up a Keras model? Just checking. Hopefully this will run maybe after lunch. I don't know.
Aaron, just sort of like a general question. I guess, is some of this sort of work then, like, because obviously it's quite computationally expensive. Like, I mean, is it going to like restrict sort of individuals unless you've got like high spec machines or you work for like Google have got the resources? I mean, does that affect people who sort of might want to do this sort of research, or you just have to put up with like slower times or stuff?
Yeah, I think it does. Yeah, you could put up with slow running on. You can do deep learning with CPU. Like, it's not impossible, but like, you know, I think it's insane. Like, especially problems like this. The reason you're using deep learning is because you're not really. This is an easy problem, right? This malaria thing. We could have done this for k-means clustering, couldn't we? It was really simple to that lesions example. When you're doing stuff like this, you would never really want to do CPU. It's not impossible. So yeah, you are limited. This code at the moment runs fine, or it did in September. It ran fine on my laptop, but again, my laptop is a Dell XPS. It's got a dedicated GPU, and it can run this code within about an hour and a half. Obviously, it can't record my Zoom mic, which I'm just, I don't know why that is. But yeah, it definitely is a limitation. And, you know, at Sale, again, if you wanted to do deep learning, if you're thinking for your dissertation, you really want to do this, you know, we have GPU clusters within the Sale data bank, and Marcos uses those quite a lot in his research. You do need access to that kind of architecture, really. Any other questions? I know it's coming to the end of the week now and our brains are all hurting.
And just like a follow up on this, in case if you want to revisit the lab in a way, is there a way to like, you know, chat about it sometimes after this week?
Okay, yeah. So first thing, you can contact me whenever you want. Like over the last year, I've just been like arranging Zooms with people whenever. So if you want to chat about anything in particular, just drop an email. We can Zoom, share screens, go through a notebook. That's fine. The second thing is that we do have a tutorial. The date is on Canvas.
I think it's 1st of April. 1st of April.
Yes. Thank you very much. Yeah. So we will have a tutorial. It will officially it lasts 2 hours, and what, you know, I don't come and present anything in the tutorial. I presented all I wanted to present. What I will probably do though this time around is once I fixed, you know, things like this notebook, I'll probably just briefly show you the output of that notebook when it's fixed in the tutorial. But the idea of the tutorial is you come to me, anything that you didn't explain, I will try and answer that. And by the end of the tutorials, what we usually end up doing is talking more philosophically about machine learning, and then go into, I want to do this, my dissertation, how would I approach it? So we start talking more generic advice like that. But yeah, if you have any particular issue with a notebook, just drop me an email and we'll find a time to Zoom and go over the notebook.
Okay. Okay. Thank you. That helps.
I've just got a question. It's not specifically on this. I think we discussed quickly the other day of how to, for the ROC curves, how would you reset the sensitivity? And you said you were going to update one of the.
Oh, yes. Yeah,
notebooks.
sorry. I was trying to fix this problem instead. So yeah, I do need to get around to that. And you can do it again. I will hopefully, but at the very earliest or latest rather, this weekend I'll be beavering away, just getting every notebook in ship shape so it's all working. Well, I mean, they all work apart from this one. But yeah, I'll definitely do that. It's on my list. Also, regarding video recordings, this is actually a bit of a nightmare for me at the moment because one thing, even though the mic has been great, I'm on the PC labs in the data science building, and I can't be here past 5 o'clock. So by the time I close Zoom down, it takes an hour or so to convert the video, and then you have to take another hour or so to upload. So I can't do that in the evening. So I'm going to have to upload this next week. I've looked back at some of the previous videos, and yeah, I'm just really not happy with the mic quality. So what I'll do is I will re-record those slides and put those up as well. So yeah, I apologize about that. It's yes, squeezing all of this into 9 to 5 to do all the Zoom and the recordings thing has been a real challenge for me. So I'll there's still a list of things to sort out, and starting from this weekend, I'll get it all ship shape.
So Aaron, before you finish off, like a general question, like related to this, what would be your time period when would these algorithms will replace, let's say, a radiologist or a pathologist?
Sorry, I didn't quite catch that. Can you repeat?
So all these algorithms, like you are classifying, let's say, in the X-ray with pneumonia and X-ray without pneumonia. I think those are those jobs are done by radiologists. Like, what would be your time frame? When would let's say these algorithms replace radiologist or a pathologist? Or is
I see. If they would replace a pathologist
or a radiologist? These
or
are
a radiologist, yeah.
by radiologist.
Yeah, so that's an interesting question. There was a paper which came out about 3 years ago where a deep learning network was trained to identify skin lesions and classify them, and it performed better than the average opinion of something like 50 dermatologists. And yeah, I think it's an interesting scenario because maybe about 10 years ago, we didn't really trust it. The black box thing came into play. Oh, we don't trust this, always trust the doctor and so on. But, if you know that you have a machine learning or deep learning algorithm, whatever it is, that has outperformed 50 different dermatologists, and, you turn up at a clinic and you're not offered your data to go through a deep learning network, which, you're aware has done really well. I've heard conversations about things like, well, I'm going to sue the hospital then because I'm not getting the best opinion. And it does go into some really interesting scenarios about should we be running this as like a second opinion? So you get your doctor's opinion and you run it on this. I think we are entering that phase now, and that's purely because these are data-driven approaches. There'll be micro signals across whatever data set you're using, CS database data, images, whatever. There's micro signals in there that humans just don't pick up, and they actually do help. Noisy micro signals that, as a whole, they do contribute to the decision boundary. So, will they replace? I don't think they'll ever replace. That's my opinion. Are there any clinicians here today? We do usually have clinicians on this course.
Yes.
So what's your opinion?
Okay. It's I think it's complicated because even a clinician can't know everything itself. Our knowledge isn't always as vast as people would like to think.
Mm-hmm.
Even sometimes you still have to go back and look at the textbook just to be sure what you're looking at.
Sure.
So if it helps, it helps. Well, can't really say much. I can't say neither this or this. Well, you know more about that, though, don't you think?
Yeah, well, I think at most they will only ever be used in conjunction to assist, if clinical decision support. I think that's as far as it will go. I would, yeah, it would never replace a clinician. Like I just can't see that ever happening. That would be insane to me. But
yeah, but the question is, in places where this specialists aren't available, then what do we do? Like, isn't that where technology helps?
Yeah, it does. But I think I think a lot of work goes into filtering things. So just from my my PhD, the idea was to use machine learning to look at the 3 million variants each person has that are different from what their parents' genetic code. And across those 3 million variants, any one of those could cause a disease, could cause disease, one of those mutations. So you have to use machine learning to filter those down because you can't look at every single one. You can't pass everything through a wet lab. So bioinformatics was a field which really early on accepted machine learning for that reason. And I suppose in clinic, you would have filtering done in that way. I work with natural language processing a lot more than I do image. I don't really do that much image classification. And I'll demonstrate this afternoon a tool that we've built that allows clinicians to annotate their clinic notes so that a machine learning technique, which is actually LSTM, which is what I'll demonstrate in the notebook, can predict where a prediction is, where like a prescription or a mention of a seizure frequency is within a document, and tell you how many seizures they're having per week. And the idea is that the clinicians, they can input their expert knowledge to form training data, and then we will train that. And where we are at the moment with that is clinicians seem to be excited about it. There's a lot of buzz around NLP in healthcare. I think people are still afraid to discuss when do you let the machine take over, or do you let the machine take over? So we're just all academics in this field trying to improve these things. But yeah, at some point we have to have this conversation. I don't think we're ready for it yet, though. I don't want to cop out of the question, but yeah, that's my only thoughts really. I think we're not really. I don't think we're really there to start talking about that. I don't think we ever will. I think it'll only ever be used in conjunction with expert opinion, and they'll just weigh it up.
Yeah, the thing is, like over there, doctors are more widely available, but in more places like, sub-Saharan, where doctors are few and clinician specialists itself are fewer found. So recently, it wasn't last year that I saw that there was, AI deep learning used to create a machine that can help easily diagnose some like common causes of blindness. And they took that to sub-Saharan so it would be easier, because most of the time to see an ophthalmologist would be very difficult in some areas. You can go 3 states and still not see an ophthalmologist there. So that was where the technology came in handy.
So yeah, I think that's a good example. Which, I mean, obviously, being in the UK, we probably don't think like that, and I think that's a good example where, if the choice is of just not getting diagnosed at all, and a decision being made by a machine, which I guess around 80% accuracy, then yeah, sure, you would make use of that instead of where something doesn't exist. But I think the original question was, would machine learning replace dermatology or whatever, pathologists, dermatologists, and I don't really see it replacing it. If you have no option, there's no option there. As you said, that there is no dermatologist available or ophthalmologist, then yeah, I guess it does make sense just to use a machine learning model and maybe refer on if it's saying a patient, I don't know, has identified a growth or cyst or something in someone's eye, and then you have to prioritize who gets sent to a central hospital somewhere, then yeah, I think yeah, you it would be fine to do that.
So Aaron, in this model you trained with, let's say, the image recognition for cat and dog, cross implementation. How much of it is like helpful, and let's say how much of it reduces the overall training percentage from, if you want to purely train on this X-ray model only? Like, what would be the difference you find when you use the uh, the training from the other model?
Sure. So yeah, I can answer that because yeah, when I run this back in September, and I did use the pre-trained weights with the GPU turned on, this whole notebook would run in about an hour and a half. And because I just obviously, the running the whole course 9 to 5 and so on, I just didn't really get time to. I found out what the issue was, but just fixing it, actually rerunning the notebooks and so on, I couldn't do it. So what I had done is I just removed this so you don't use the base. And as I said, I started running that on Wednesday night, even with the GPU. Wednesday 8 o'clock. By about Thursday midnight, yesterday midnight, just to check if it had run. I was praying that it had run earlier. It still hadn't finished training, so clearly there is a massive difference in computational time and how expensive it is.
Mm-hmm.
And it still hadn't converged. So all I could tell you was that about maybe 30 hours later, it still hadn't, and I can't tell you how long that would have taken to go. No, actually, it was on something like 20 out of something epochs, so that gives you an idea.
Mm-hmm. So is there any difference between accuracy level, or both model will give you equal accuracy, same accuracy?
Yeah, so I've never run this without the base because of the reason I just said. But that would be something I now would be interested in doing. Clearly, the fact that people use these often, there's so much effort gone into creating a resource like this. I don't think people would do it if it was rubbish. That's the only way I can think about answering that.
Why I asked this question is like, with healthcare data, it more becomes like how much of it is false positive and false negative. So like you said, we have to be very sure about false negatives. Like, those are very important when it comes to healthcare context. So
that's true. And but here you can specify that you want to optimize on. So is it Fergus, I think, mentioned genetic algorithms. I reckon you can probably optimize this with a genetic algorithm. But anyway, yeah. So you can optimize on sensitivity or specificity or precision recall. So yeah, if you as you've said, the false negatives or the true positives, they're really important. So you could optimize on that instead.
Yes.
So sorry, if you're trying to tell between, like I said, no pneumonia, COVID.
Yeah.
Would that base still work?
Yeah, it would. Yeah. Okay. So you could add a third class here. This flow image from directory, you're telling it up front, just ingest a load of images in a certain way. And we're saying, look, here, there is a directory called normal. And directory called pneumonia. If you had a COVID one, I'm going to try and find it actually. Yeah, here we go. Yeah, so this started during the pandemic, and okay, yeah. So yeah, these are different categories. There's clearly multi-label. We've seen 3 already. So yeah, you can set this up. And as I said, a good way to learn this is deep learning. It's just, you can see the hotness or whatever. I don't really know how this metric's worked out as such, but you can click on people's notebooks to see how they're solving it. Most of them will be in Python. Reasons I discussed. I wonder if there's an R implementation. Filters are no. So I suppose those people that do Python that might be quite comforting, but you can do this in R, yeah. But all you do is just add in a different class there, and it turns into a multi-label problem.
So since it's just like the base is trained on just telling the difference between cats and dogs, wouldn't affect the learning itself.
Sorry, didn't quite catch your point there.
Okay, like since it's trained on just 2 categories, telling the difference between cats and dogs, it won't affect if you increase the amount of categories later.
Oh yeah, so yeah, it will. The more categories you add in, it will make it harder to do. The main thing to think of there is that the more categories you add in, the more data you will need to collect to spot the trend. So yeah, multi-classification problems, they are more difficult than binary, definitely. Where am I?
Aaron, in the notebook, the accelerator setting, it says it requires a phone verification. Is that something necessary, or is there a way we can change it? For setting up the GPU.
Oh, this, yeah, here.
Is it from the environment option?
Yeah, it's an option, just a drop down. If I click none now, it'll probably turn it off. But yeah, this is a drop down option.
Okay, yeah. So where it shows none for you, right now?
Yeah.
It shows me that phone verification is required.
Phone verification?
Yes. I'm not sure if that's because, it's your notebook, or because I need to sign in or something into Kaggle.
Probably a Kaggle sign in. I don't think I can do my notebook because it's public. Anyone can just take this.
Okay. Okay, so I think if I sign in, that should go away. Is that the case?
Yeah, I would have thought so. Yeah.
Okay. Even if you do sign in, you still do need to verify with your mobile phone, I think.
Okay.
I don't know why that is.
It's not a big deal. Like it's really quick. You just need to click it, put your phone in, and it sends you a code. That's it.
Cool. Thank you.
So, are there any other questions about CNNs? We're going to look at RNNs later, which is sequence data, which are actually, they're more difficult to get your head around than this. Or should we go for lunch? Okay. So, let's go for lunch. Cut to 1:15. So, so we'll come back at 1:15. I'll go through RNNs, which is what I tend, that's more what I do. And then after that, we'll just have a slight coffee break. And before we go today, I will just very briefly show you the assignment. I'll set the assignment at the end of the day. And as Pete said, any feedback that you want to give about this module, I'll stay right till the end and take all the feedback in. And I've had some really useful feedback over the week. So thank you so much. So yeah, that's the schedule for the rest of the day. And as I said, we'll come back after lunch at 1:15.